Hello, hello. We are starting our next unit on probability distribution. So we're continuing with the idea of probability. And this is the beginning here, section 6.1a on introduction to probability distribution functions, also known as PDFs. So our goal today is I can recognize valid PDFs and work with them. So a little bit of a review. A probability model is something we've worked with before. There's different types of models, but a probability model describes the possible outcomes of a chance process and the likelihood that those outcomes will occur. So let's just take an example here. Consider tossing a fair coin 3 times. We're going to say X is the number of heads obtained. So we don't know how often we would get heads when we do this situation. Now, if we think about it, there's different models that we've shown to figure out all those outcomes. So we got to figure out how many outcomes there are first of all. For one flip, you can get a heads or tails. Another flip, you can get heads or tails again. Right? That's still only 2 flips. No matter what you start with, there's still only one more flip. So we need a third one. And again, heads, tails for each of those, which will create 8 possible tracks for how your coin flipping could go. So ultimately, that gives us a sample space, is what we call, of all the possible outcomes. So our sample space is, let's list them. We've got heads, heads, heads. We've got heads, heads, tails. We've got heads, tails, heads. And you can just go right down the list. Oh, heads, tails, tails. And 2 more. We got tails, tails, heads. And then tails, tails, tails. So there's our sample space. It's just showing all the possible outcomes. We also want to know the probabilities of each one happening. And we're talking about number of heads being obtained. So we can show that a couple different ways. Number one is what we're going to use probably the most, especially today. It's just a little table of X being the number of heads. So really, you could get no heads. Here's an option for no heads. You get 1 heads in here. Is there any other ones with 1 heads? Here's one with 1 heads. You get, oh, here's another one with 1 heads. You get 2 heads. We got 2, we got 2, we got 2, and you get 3 heads. So those are our possibilities for number of heads. So we're going to put those 0, 1, 2, 3. Now, the other part of a table like this, you have to show the probability of getting that X. Okay, so 0, there's 8 total possibilities. There's only 1 out of 8. If you want to write it as 0.125, that's also the same thing. There's 3 out of 8 here, 3 out of 8 here, and 1 out of 8 here. So that's one way to display. It's one probability model. It shows all the possible outcomes and their probabilities. We've kind of looked at things like that before. But let's show one other way that we've also done. You can make it into like a histogram. Okay, where this is going to be our X, our number of heads. We could have, let's just divide it up here. 0 heads, 1 heads, 2 or 3, and then we want their probabilities. Let's just say that goes up to 1/8, and we got 2/8, we got 3/8, and I go, of course, the bottom is 0. So for 0 heads, it kind of happens 1/8 of the time, so we're going to go up to here. 1 is up to 3/8, 3/8, 1/8, and we've got ourselves a histogram. Now, we can also describe this histogram. We can kind of sock V it, or just talk about the shape. This is symmetric. This is, I would say, unimodal. We don't know that it's perfectly normal. It kind of looks normal, but we'll go with this. So, but this is the point, is we have different probability models that we can look at to display data dealing with probabilities, or display possible probabilities. So we're going to talk today about random variables as opposed to just regular variables. and also how that applies to probability distributions or probability models. So a random variable takes the numerical values that describe the outcomes of some chance process. So we're talking about numerical values as opposed to, maybe in the past we would do like, you could get heads or tails, you know? And what's the chance of each? But now we're shifting to the number of heads and the number of tails. And you saw that in our probability model, it was the number of heads that we got. That was our x. So that's kind of our shift now. A probability distribution is of a random variable, gives its possible values and their probabilities. So we essentially made one of those in our table. So there are really two types of random variables, discrete and continuous. We've talked about these terms in the past, and we're bringing those back now. So a discrete being random variables that have gaps. So they're only whole numbers. You could potentially have a decimal point if you're doing like shoe size, where you have 7, 8, but you can have a 7.5. It just can't have all the in-betweens. Whereas continuous, there's no gaps. Okay? Discrete is gaps, continuous is no gaps. So different examples of those. Let's identify the following random variables associated with as AP Stats as shoe size, as discrete or continuous. So the first one I have is shoe size. Well, that would be discrete. I just said that. That is discrete because it cannot have all the in-betweens. You can have 7, you can have 7.5, you have 8, and so on. But you can't have like 7.3. There's no continual numbers there. Whereas foot length, that goes with shoe size, foot length, you can have any foot length. You could have 7.425 inches of feet, so that is continuous. All right? Jean size. Jean size is, I mean, it depends on if you're wearing like men's or women's jeans, but like it might be size 2, 4, 6, or kid size. But there's not the in-betweens, so this is a discrete random variable. Discrete. Whereas waist circumference could be anything. That is continuous. You can have the in-betweens. We got 2 more. I can't spell. Continuous. Sorry about that. GPA and class rank. GPA, you can have, like if you look on your Infinite Campus, you can have a GPA with several different decimal points. It is continuous. And some of those are even rounded. Whereas class rank, you literally are number 1 in your class, number 2 in your class, number 3 in your class. There is no 2.5. So that is a discrete random variable. Now, what's the difference between a regular variable and a random variable? I want to talk about this real briefly here. That's not what I wanted at all. Here, let me fix that. So a discrete random variable is, a regular variable x is usually lowercase. You can actually solve it. You can figure out that x equals 7. It actually has a value to it that's like set. You might not know it at the beginning, but you can figure it out. So it represents a constant number that we don't know yet, but it already exists and we can solve for it. Whereas what we're talking about now with random variables typically are going to be used as a capital X. So keep that in mind. This is going to be a capital letter. You'll see that. And it's something that hasn't even occurred yet. And so it can be multiple different things. Each outcome has a probability of occurring. It's not a set number that we're trying to find. It's just a thing that could happen. So our random variable is going to be like 0, 1, 2, 3 times like of getting heads, and then the probability that goes along with it. So there is a difference between a regular variable and a random variable. In this unit, we're focusing on these random variables. A couple things with probability, though, just as a reminder. When we're using discrete probability distributions or probability distribution functions is the PDF part of it. But I'm going to focus on the discrete. It's again listing all the possible outcomes and their probabilities. They're numeric outcomes. And same thing happens. All of the probabilities have to add up to 1. So all of these probabilities Like these have to, sum to 1. Their sum is going to be 1. That's just the way it is with probabilities. And they're always going to be between 0 and 1. You can't have like a negative probability. You can't have something bigger than 1. They all add up to 1, so they're going to be between 0 and 1. So let's look at a couple examples of either using these or creating these probability distributions. So number 1, it says if you randomly select a jail inmate convicted of a DWI, the prior distribution for the number of, the probability distribution for the number of prior DWIs is listed in the table. Okay, so what this means is X is the number of prior DWIs they've had before getting convicted. So part A says explain the meaning of the random variable of 0. So if capital letter X equals 0, that just means that that a randomly selected jail inmate convicted of a DWI had 0 prior DWIs. And it says that happens over 50% of the time. So 50% of people convicted had 0 prior ones. It's a first-time offense. But that's what that's saying. At X is 0, the probability is 0.51. That means 0 prior DWI sentences. So what is the probability that an individual selected at random would have 2 prior DWI sentences? Okay, well, then we're saying with this one, we want to actually state the probability of X is 2. We can go straight to our table and say it's 0.132. Now, on an exam, I would say you should explain that. That's 13.2% of, 13% chance of, or some wording like this, of a randomly selected inmate convicted of a DWI had or has 2 prior DWIs. That's what that means. Okay. So last question I've got for this one, find the probability of X being less than or equal to 1, meaning they have at most 1 DWI. So if I'm going to say the probability of X, capital X, being less than or equal to 1, that is truly the probability of X being 1, or, I'm saying it's less than, so yeah, or 0. So we would add the probability of X being 0, because it's at 1 or less. So really, that ends up being 0.512 plus 0.301, which gets us 0.813. And you can state that's 81.3%. You can say all the same stuff. Had at most 1 prior DWI. All right? So that's how we're going to look at a probability distribution and kind of figure some things out based off of that. Now, what if you're not given the probability distribution? Like, here's a situation. Car headlight manufacturers. They're concerned about failure rates. So one headlight failure is an inconvenience, but if both are out, then you really can't drive at night. So assume that the probabilities of 0, 1, or 2 failures are 0.96, 0.036, and 0.004 respectively. Create a table to illustrate this. Okay? So we want to always first state what our X is. What is our variable, or whatever, if you're going to do F for failures, but really it is the number of failed headlights in a random car. All right, so if you want to change the variable to F or H for headlights, whatever it is, we want to then make our table. So X is our possible number of failed headlights, which you can have 0, 1, or 2. There's no more than 2 headlights on a car. And then we want the probability of getting X. So let's just fill in this table real quick, and then we'll answer a couple questions based on that. So it was 0.96, it was 0.036, and 0.004. So if you have that information, explain the meaning of the random variable having value of 0. X equals 0. Well, same deal. No failed headlights. Both work. So the car has no failed headlights. Happens a lot of the time. It's a good thing. Headlights. They both work. Find the probability of exactly one headlight failing. That's exactly 1. That's X equals 1. So the probability of X equaling 1, that is simply given in the table. It is 0.036. And you can put that into words. Okay? You can say 3.6% of the time you have a randomly selected car with exactly one failed headlight. Okay? So this is what we're working with. I have one more example, but we don't necessarily need to go through it. It's kind of like the last two. Consider the probability distribution associated with the number of girls in a family of 3 children. So again, you could have up to 3, so you'd make this table of, you could have 0, 1, 2, or 3 girls. To find those probabilities, you just make you actually can go right back to our example of our tree diagram here, and just instead of heads and tails, it's boy and girl. So you can see all the different combinations. You can actually use these exact probabilities, 1/8, 3/8, 3/8, and 1/8. It's the same situation, just boy and girl instead of, heads and tails. But that's the idea that I want to introduce you today of probability distributions, probability distribution functions, PDFs, or discrete probability distributions. So that's section 6.1a. We'll see you next time.